Yes, so yes. So let's move on towards our next topic. Okay, before moving on to next topic, we had seen in the previous class that what we had seen, if I am writing it in another form, the thing which we had learnt in the previous class, I am writing the same thing in some other form now. Okay, so writing it in some other form, we get like this. If psi I and psi j are two independent solutions of Schrodinger equation or wave functions, okay, they are two independent solutions of Schrodinger equation, or either they can be called as wave functions, okay, two independent wave functions. Now, what is the meaning of independent wave function or independent solution? I am going to tell you now, okay. Then these functions are normalized if, okay. Why triple integral? Because volume integral is being taken, right? So whenever we take the volume integral, it is basically triple integral. You might have learnt in your BSc maths, or if you had maths optional in your previous attempt, in case you had maths optional in your previous attempt, or in case you might have learnt in BSc, that triple integral simply implies that it is basically volume integral, right? It is basically volume integral. Yes. So now the meaning of this is conjugate basically. Okay. The meaning of this is star. On the top of this there is a star, right? The meaning of that star is basically conjugate. I had told you in the previous lectures that the meaning of conjugate is that you will replace I by minus I. Suppose suppose I have wave function psi 1 equal to e to the power I e by h cut, okay, x. Suppose this is my uh, uh, wave function number 1, okay, x t, okay. Suppose this is my wave function number 1. If I want to find its conjugate, if I want to find its conjugate, then what will I do? I will write it like this. I will put a star over here, okay, in order to find its conjugate. And simply in order to find conjugate, I will replace I by minus I, okay. So when I replace the I by minus I will get it to be like this, okay. So I has been replaced by minus I. Similarly, if I say the reverse way, if this is my wave function, okay, suppose this is psi k, then in a similar fashion this will be its conjugate, which will be called as psi, okay. Let me write capital psi because it is time dependent one, so it will be capital psi k star, okay. So that is the meaning of basically conjugate. So the terms that you see over here, this term is conjugate of this, or this term is conjugate of this. So both are basically conjugate of each other. And d tau is your differential volume element. I have already told you in the previous classes that d tau is your differential volume element, and you are integrating it over all space. All space simply means that you are integrating it over the entire volume, and entire volume simply means that you will take triple integral in order to denote volume. Just remember this thing, that integration over a line is single integral, okay. Whenever we integrate over a line, it is single integral, okay. Whenever we integrate over an area, it is double integral. and whenever we integrate over volume, it is triple integral. Okay, this thing you have to remember. Okay, so psi I and psi j are two independent solutions of Schrodinger equation, right? And what is the meaning of these independent solutions? Some students don't get this. Okay, so if psi I and psi j are two independent solutions of Schrodinger equation, what is the meaning of this? I already told you in the previous class. I already told you in the previous class that it is given to us that psi I and psi j are the solutions, right? It is given to us that these are solutions of Schrodinger wave equation. This is given to us. Now the thing is, I had already told you in the previous classes that multiplying by a constant, okay, multiplying by a constant or dividing by a constant, okay, or simply not addition but multiplication division, or something like this, okay, it will not change the nature of the function, because c square is again a constant, 1 upon c is again a constant. Okay, so multiplying or dividing by a constant does not change the nature of the function, right? And as it does not change the nature of the function, if these two were satisfying the Schrodinger equation, their solution of Schrodinger wave equation just implies their solution of Schrodinger wave equation just implies that they satisfy the Schrodinger wave equation. Okay, psi I and psi j are solution of Schrodinger wave equation simply implies that psi I and psi j satisfy the Schrodinger wave equation. So if psi I and psi j satisfy the Schrodinger wave equation, that it simply means that we can make innumerable combinations. We can make innumerable combinations. Innumerable combinations. Innumerable combinations of what? We can make innumerable combinations like this. Like psi I is there, then we will write c psi I, we will write c2 psi I. Okay, so there are innumerable means infinite such combinations possible, because I already told you that multiplying or dividing by a constant does not make any difference. Okay, if psi j satisfy the Schrodinger wave equation, then c psi j will also satisfy the Schrodinger wave equation. If psi I satisfy the Schrodinger wave equation, then psi I by c will also satisfy the Schrodinger wave equation. Okay, if psi I satisfy the Schrodinger wave equation, then this will also satisfy the Schrodinger wave equation, and this will also satisfy the Schrodinger wave equation. Okay, because they are only multiples of it. If this satisfies the Schrodinger wave equation, then c psi j will also satisfy, c cube psi j will also satisfy, and there are innumerable such combinations possible. Okay, so these independent wave functions. Let me ask you one question: are the wave functions like psi I, c psi I, okay, 3 psi I, okay, psi I by 3, okay, are they independent? Are they independent? Answer is no. They are dependent. They are not independent. Okay, they are not independent, because by multiplying or dividing by a constant I can obtain it. So they are not independent wave functions. Okay, they are not independent wave functions. But over here it is written that psi I and psi j are two independent solutions of Schrodinger equation. It simply means that psi I and psi j are not related like this. Okay, this psi I which I see over here, this psi I which I see over here, and this psi j which I see over here are not at all related like this. Are not at all related like this. For example, if someone is very someone is very naughty, then that naughty person, what will he do? He will write psi j equal to c psi I, and we'll say that psi I and psi j are two solutions of Schrodinger wave equation. But are these independent solutions? Psi I and psi j you are taking differently, and you are also saying that psi j and psi I are related like this. So are they independent solution? The answer is no, because C is a constant like 1, 2, 3, 4, half, etc. Okay, so basically they are not independent solutions, because this psi j clearly depends on psi I, and they are related by this relation. Okay, so they depend on each other. But over here it is saying that are two independent solution of Schrodinger equation. Independent means both of them cannot be written with the equality sign between them. Okay, like this they cannot be written. A relation like a relation of this kind, a relation of this kind cannot be written between them. A relation like this cannot be written between them. Okay, so that's why we have written the thing that are two independent solutions of Schrodinger equation, or they might, or we might also call them independent wave functions. Okay, because dependent wave functions will simply mean that you can obtain the other wave function by simply dividing or multiplying by a constant. Okay, so independent wave function will also imply the same thing. Okay, so psi I and psi j are two independent solutions of Schrodinger equation, or they are independent wave functions. Then these functions are normalized. Okay, then how will these functions be normalized? Then these functions are normalized. These functions are normalized if this relation, if they satisfy, then these functions are normalized. Okay, this is the relation which they must satisfy, so that they are normalized. Okay, you got it, right? And one thing I want to tell you before moving on to this class, that if someone of you is new to the channel, if someone amongst you is new to the channel and who hasn't watched the previous 14 videos, then I kindly request you to please go and watch the previous 14 videos. The link is there in the description, and the link is also in the form of comments. Okay, so you can go and watch the previous 14 videos, and then you can come to this 15th video, so that you are able to understand the things better, because this lecture series is going on in sequence. Okay, this lecture series is going on in sequence, that's why I am saying. Okay, so if psi I and psi j are two independent solution of Schrodinger equation of wave function, then these functions are normalized if they satisfy this relation, this particular relation. Okay, and also there will be, and both of these are I. Okay, not one I and another j, both of these are I only. Similarly j will also satisfy similar relation. Similar relation will be satisfied by j also. And j, what will the relation in case of j look like? Okay, dicto the same. In place of I only you will write j. Okay, so you will write basically j. Okay, so this is the thing which you wrote. Okay, d tau is equal to 1. Okay, so this is also for all space. So this was for j, this was for I, and this was for j. Okay, so they are being integrated over all the space. So they satisfy this relation independently. And let me tell you one thing, if you think that if these are not independent, okay, suppose if these are not independent, over here it is given that they must be independent, but suppose if they are not independent, then will they satisfy this relation? Yes, they will. It will become obvious. Okay, then it will be obvious. If they are related like this, that means if they are dependent wave function, na, if they are dependent wave function, then this is statement. If they are dependent wave function, then this is statement. Okay, and this is statement are quite obvious. Okay, and they will be the same equation actually. That's why it is given that we should write two independent solutions, so that we make some sense out of the sentence. Okay, we should make some sense out of the sentence, right? So that's why it is given that two independent functions are required. Okay, so hopefully you got up to here, you got everything up to here. Now let's move on towards our next topic, which is orthogonal wave functions. Okay, let's write over here orthogonal wave functions. Orthogonal wave functions. Okay, so let me write over here, if two wave functions psi I and psi j, okay, if two wave functions psi I and psi j are such that, if two wave functions psi I and psi j are such that they simply this is triple integral for all space, that means volume integral. Okay, this is what is the volume integral, which will look like this. Okay, d tau is equal to 0. Okay, so this is the, now don't get confused over here. Okay, this is the first relation which is being satisfied, and another relation which is being satisfied. Okay, and another relation that is being satisfied is all space psi j star psi I d tau, okay, is equal to 0. Okay, and the condition is that I should not be equal to j. The condition is that I should not be equal to j over here also, and I should not be equal to j over here also. This is an important condition. Okay, okay, so then if they satisfy these two conditions, then they are said to be, then psi I and psi j are orthogonal wave functions. Okay, now orthogonal wave function, let me explain properly to you. If there are suppose two wave functions psi I and psi j, again they are independent. Psi I and psi j are independent. Okay, and they are such that they satisfy this relation. Okay, and the other relation which they satisfy is this one. What are the relation? Basically, the relation is that when you take the conjugate of this, and multiply it with this, okay, or when if you take the conjugate, see, suppose, okay, let me write over here. Okay, let me write over here that suppose psi I is there and you take its conjugate. Okay, if you take psi I's conjugate and multiply it with psi j and integrate it over the volume, then it will yield you 0. For example, I have taken the conjugate of psi I and multiplied it with psi j, and I have taken the volume integral over all the space. So conjugate of psi I multiplied by normal function. Normal function means without conjugate. Okay, so conjugate of psi I multiplied by psi j function taken over volume integral, that will yield you 0. And similarly, this function taken original function and the conjugate of this is taken, then it will again yield you 0 when you take the volume integral. So that is the thing which has been written over here. Okay, now don't get confused between the two conditions. The two conditions I have already told you. In this condition was a very different condition. Why this condition was very different? Because you know this na, this condition was very different because you are taking psi I and you are multiplying with the conjugate of itself. You are taking psi I and multiplying it by psi star I, and you are taking the volume integral. It is yielding you 1. Okay, it is yielding you 1. When you take psi I and take its conjugate, you multiply both of them and take the volume integral, then you get something equal to 1. Okay, so psi I and psi j are basically conjugate of each other over here. and you are taking the conjugate of the same function and multiplying it over here, right? But in the this thing over here, you are taking the conjugate of the another function and multiplying by this function. So j I is not equal to j. Clearly I is not equal to j. As I is not equal to j, so it is quite clear that this is orthogonality condition, because you are taking the conjugate of different function. What will happen if I will become equal to j? If I will become equal to j, then you will simply put I in the place of j, and if you put I in the place of j, it will become normalization condition. It will not remain orthogonal condition. It will not remain orthogonal condition. Okay. Similarly, over here, if you simply, if this is the condition, this will hold good. But as soon as you take I equal to j, simply I can replace this j by this I. In that condition, orthogonality will not hold. In that condition, orthogonality will not hold. Instead, you will reduce it to normalization condition. It will not yield you 0. Instead, it will yield you 1. Okay, so it will become normalization condition instead, right? So that's why these two things are written like this over here. Okay, so this is the thing. Now, what are orthonormal wave function? Okay, orthonormal wave function are also there. Okay, so we have learned two things, right? Normalized wave function and orthogonal wave function. Okay, now what are orthonormal wave functions? What are orthonormal wave functions? Orthonormal wave functions are nothing but they are both, okay, they are both normalized and orthogonal. Okay, if they are both normalized as well as orthogonal, they will be called as orthonormal. Okay, if the wave functions are both normalized as well as orthogonal, they will be called as orthonormal wave functions. Okay, so how can we write the orthonormal wave functions? How can we denote them? How can we denote them? Let me write over here that I had already told you that this thing, okay, this thing yields you 1, right? This thing also yields you 1. This is what is normalization. Okay, normalization. Now what is orthogonality? Orthogonality is nothing but like this. Okay, orthogonality is nothing but like this. Okay, this is the condition number 1 and this is the condition number 2. Okay, where this I is not equal to j. Okay, I is not equal to j over here, because if I will become equal to j, if I will become equal to j, then it will reduce to this condition. This will become this condition will, if I will become equal to j, and if I becomes equal to j, then 0 will not be there, 1 instead 1 will come. Okay, that's why it is written like that. Okay, it is, that's why this condition has been imposed that I is not equal to j. So these are what? These are basically orthogonality condition. Okay, this is what is orthogonality. Okay, this is orthogonality and this is normalization. Then what is orthonormality? Orthonormality means, orthonormal simply means that all these four conditions will be satisfied simultaneously. Okay, एक साथ satisfy होगी ये सारी condition. If all these conditions from the top till the bottom, if all these conditions from the top till the bottom, okay, all these conditions from the top till the bottom, if they are satisfied simultaneously, if they are satisfied simultaneously, all these four equations are satisfied simultaneously, all these four conditions are satisfied simultaneously, then such a situation will be both normalization and both orthogonal, both condition will hold. So if normalization and orthogonality both of them hold together, that means all the four equations are satisfied. In that condition, such a condition is called as orthonormal condition, and this orthonormal condition is denoted like this. Those, instead of writing those four relations again and again, instead of writing those four relations again and again, I will simply write it like this. I will simply write it like this, equal to delta ij. Okay. Now what is this delta? This delta is basically your Kronecker delta. Okay. This is basically your Kronecker. This is basically your Kronecker delta. Okay. So this ij. Now you only tell me that when I will be equal to j. Okay. Suppose if I equal to j, suppose. Okay. Suppose I equal to j, then simply you can write I over here instead of j. As soon as you write I over there instead of j, so what will this turn into? It will turn into 1. Okay. So for I equal to j, this value will be equal to 1. And when I is not equal to j, then such things cannot be written. Okay. Such things cannot be written. Then I and j will be independent of one another. Right. And if I and j will be independent of one another, then clearly this condition will hold good. The condition which is given in the bottom, when I was equal to j, this condition will hold good, and the result will be 1. But when I is not equal to j, these conditions in the below will hold good, and it will yield you 0. Right? So basically, when I is not equal to j, this Kronecker delta will become 0. Okay. So when I is not equal to j, this Kronecker delta becomes equal to 0. Now what is this Kronecker delta? You might have learnt in your BSc mathematics. In your BSc mathematics, you must have learnt what is Kronecker delta. You must have learnt over there. Okay. So that is the thing. Okay. So you don't have to go into how Kronecker delta is defined. Kronecker delta is nothing. Okay. Kronecker delta is nothing but such a delta. Okay. It is such an integrand. Okay. It is such a thing that it will yield you 1 when I will be equal to j. Okay. So what will it be? It is like this. Okay. When I is equal to j, it looks like this. And if I is not equal to j, it looks like this. Okay, like this. If I is not equal to j. Okay. So if I is not equal to j, it will become 0. And if I is equal to j, then it will turn into, this will turn into this. Delta I, delta jj, like that. And its value will be equal to 1 when I is equal to j. Okay, so just remember this thing. And these are called as orthonormal wave functions. Okay. All these four conditions which have been written on this screen, have been clubbed. All these four conditions have been clubbed in a single equation, and with the help of a single equation we are able to denote all these four conditions over here. So that is the advantage of this Kronecker delta. And how Kronecker delta is defined? Okay. How Kronecker delta is defined? So part of maths optional syllabus, not physics. Part of maths optional syllabus, not physics optional. Okay, it is a part of maths optional syllabus but not physics optional. Okay, so that is the thing. That's all for now. Then I will start with the PYQs in the next class. Till then अपना ख्याल रखें. जय हिंद जय भारत. हमारे चैनल को देखते रहें.